In this video, we will be discussing how to determine the average rate of a kinetics experiment using the balanced chemical equation. We will be doing two problems. The first problem says, using the following equation, determine the change in concentration for P and the change in concentration for P2O5 if the rate of O2 disappearance is 0.46 molar per second. We have a balanced chemical equation. So it's important that we go and write our fractional determination using our change in P over the change in time. So this is going to be negative 1 over 4, the 4 coming from the balanced chemical equation. The negative shows that this is a rate of disappearance. We will multiply this times the change in the concentration of P over the change in time, or our rate. We will set this equal to the rate for our oxygen. So that will be equal to negative 1 over 5, the 5 coming from the coefficient of the balanced chemical equation for oxygen, and multiplying that times the change in oxygen over the change in time. Now what we must do is cross multiply in order to get our 4 into our numerator. So this will give us negative 4 over negative 5. This occurs when you have two reactants, times our rate for oxygen, which is given in the problem. That is negative 0.46 molar per second. This is equal to our change in the phosphorus concentration over the change in time. So we have now found the average rate for just the phosphorus. If we put this into our calculator, please notice that all of the negatives will hopefully start to cancel in some way. So our two negatives of negative 5 and our negative 4 would cancel out, and we get a value of negative 0.37 molar per second. This is a rate of disappearance, so that is a good value. For our second part, we are now going to look at P2O5. So we can now do the setup of 1 over 2, the 2 coming from the balanced chemical equation, multiplying that by the change in P2O5 over the change in time. And we will now set that equal to our same term from the previous problem, which would be negative 1 over 5, the 5 coming from our balanced chemical equation for oxygen, times the change in oxygen over the change in time. So now what we need to do is cross multiply to get the 2 in the numerator of our fraction. So we can state that the change in the concentration of P2O5 over the change in time, the rate that we are trying to calculate, is going to be equal to negative 2 over 5. The negative coming from the 1/5 and the 2 cross multiplied over. So now we can determine the rate of our oxygen, which was given in the problem. So we can multiply that by negative 0.46 molar per second. In this case, our two negatives will cancel. And if we put this into our calculator, you will get a value of 0.18 molar per second. Notice that our answer is positive because it is a product. For our second problem today, using the following equation, determine the change in concentration of AlBr3 and the change in concentration or the change in time of KBr if the rate of aluminum sulfate is given and is a formation of 3.2 times 10 to the minus third molar per second. So the first thing that we need to do is establish our fractional formula. So for our AlBr3, we have a 2 in our coefficient, so we can write negative 1 over 2, change in concentration which in this case is ALBR3, over our change in time. We will set this equal to our change in concentration for the aluminum sulfate. Notice that it does not have a coefficient, so our fraction becomes 1 over 1. So we can write 1 over 1 times the change of our Al2SO43 over the change in time. If we go and cross multiply, we will end up getting -2 over 1 times the rate of our aluminum sulfate, which is our 3.2 times 10 to the minus third. So we can say -2 over 1 times 3.2 times 10 to the minus third molar per second. So in all reality, we're multiplying by -2. We will get a value of -6.4 times 10 to the minus third molar per second. So the negative shows that it is disappearing as a reactant, and we know that it is disappearing at twice the speed. For our second part, we can now set up our fraction for our KBR. Because our KBR has a 6 coefficient, this is 1 over 6, times our delta KBR over our change in time. We can set that equal to our 1 over 1 times our change in aluminum sulfate over our change in time. The bottom of our fractions come from our balanced chemical equations. So now we can cross multiply, very similar that we've done in all of our examples, and you will get a value of 6 over 1 times our rate of our aluminum sulfate formation. So that would be the 3.2 times 10 to the minus third. You will notice that I have no negative signs, so in this case our answer is going to be positive. So in all reality, we are just taking our rate and multiplying it by 6. So you'll get 1.9 times 10 to the minus 2 molar per second. In these problems, you have seen how the coefficients become the denominator in our fractional math when trying to determine the average rate of our kinetic experiments. Good luck!